Okay, thank you all the panelists for such a awesome conversation on this very important topic. Our last speaker of the day, Albert Greenberg. He's the Vice President for Azure Networking, the team that imagines, engineers, and runs the entire Azure networking stack, all the way from the NIC on the server, the TCP/IP stack running on the server, to the network in the data center, the WAN, the edge. So all of it, Albert runs. And as I mentioned earlier, Albert is also the sponsor for this event and the soul behind this event. This event wouldn't have been possible without his sponsorship. So I want us to thank Albert for the tremendous support he has provided in us being able to host this event.
Okay, so first, that was a fantastic panel. We need to do more of that kind of thing in our industry. And this is a deep technical forum, but we want to feel good about deep cultural innovation as well. So that's just one step in that journey. Well, I want to thank the speakers and all of you for coming. This is an experiment. This is the first time we've done this, and I've learned so much, and everybody was so open. And it was great to hear from Mark in the morning about using things that were born in the cloud, the whole container idea, and then bringing it to app developers to build resilient applications as we do in the cloud, and fantastic opportunities there. I mean, Najim talked about embracing the chance of failure and recovering in under a second, which is our responsibility. We heard from Aspi about the importance. Really, I wanted to give him a bear hug when he talked about it, the importance of test and making sure things work the first time in the cloud. We heard from Nick about the importance of flexibility, and from Ram about the optics tail wagging the electronic dog. And I have to tell you that I think 2/3 of my brain is that optics tail wagging the electronic dog. So I think also I just want to emphasize we're at such an inspiring time. The whole world is re-platforming into the cloud, and the responsibility and the opportunity is amazing. It's a unique time to be in networking. Networking is the reason it all works, the reason it all scales. It's the infrastructure for the infrastructure. It couldn't be any more appealing as an industry. And I really appreciate also, going back to the last talk, it's hard to collect all the dots. I mean, it's so complicated. And the diverse voice is so important for us to put it all together, a diverse and inclusive voice. One thing that came up over and over is we need to do 3 things that are hard together. Over and over today, we have to be ultra reliable, we have to be ultra agile and fast, and we have to be able to service stuff in production. That's the challenge. That is what cloud is about. And you heard it in every talk, and I'll give you a few stories on how to achieve that at scale today. And I think there's a lot more. It's a 1,000-chapter book, and we've written up to chapter 2. So, if I think about the topmost goal, and I'll give you some more examples of this, is to provide a infrastructure like the electrical grid, like any other critical infrastructure, to support mission-critical applications for the entire planet. And those of you that know in the cloud know that's for real. On the positive side, when things are working, people are innovating and growing and expanding their business and their works and lives. And when things are down, it looks like they're not working. They're not playing. The truth is they're stuck. And it's more than that. I mean, we have the critical infrastructure for health and well-being, and we're holding, the cloud is holding up pretty much the computation that supports the planet. So it is mission critical already, and it can't have glitches. At the same time, what I want to interleave in here and show that these are not incompatible goals is we want to build an open platform and an open infrastructure for building those very same applications. And I'll give you some examples today where we're sharing with the community key platform components so that you can bring it into your world, bring it into your cloud, bring it into your enterprise. And an approach that we've followed to solve these two problems and meet these two goals is to rethink network design and operations. And what I'll give is two examples. Go all the way down to the switch and rethink what runs on the switch OS, and go all the way back up to the entire network, the hundreds of thousands of devices, and think how we verify the whole network. Make sure that it does what we intended it to do. So here's an example from Azure on mission critical, and this is not the latest chart, but it's the one that was handy for me. And so we're into the hockey stick. All of the world's top companies, Fortune 500, Fortune whatever, 50,000, 500,000, are pouring their workload into the cloud. And you can count number of SQL queries per day or count whatever you want, but it's amazing. And we're in a world where, for example, in Azure, we're doubling every single year. And if you haven't lived in a world that's doubling every single year, just imagine for a minute your house doubling every single year. Half of your house is new every year. You've not seen it before. It's doing different things, and that's what it's like. You can't know your whole house in that world. You have to find another way. Okay, got some animation here. So we've been building an open platform. These are some of the companies that run in Azure, and these are some of the tools that you can use. If you like Node.js, you can use that. Really, whatever you like to build your apps is available in Azure. Linux, big time, and you just heard from Brandon about the container technologies, and we just acquired GitHub, where pretty much all the open source is created, and it's a big statement for Azure being 100% in on open source. So we're open, and we have to be mission critical. One thing that I'd like to announce here relates to this whole network verification. And I'm going to introduce terms before they're really defined, so bear with me. But if you're trying to build an enormous network with thousands of components or hundreds of thousands of components, how do you verify that it works as intended? I mean, down to the last bug. I mean, if there's a bug in the code, you want that bug to surface before you deploy the code. So you need to be able to understand that it's going to work as intended before deployment. And there we use an emulation technology it's incredibly faithful. It's so faithful that if you somehow went to sleep in the morning working on the real network, woke up, there you are on the emulator, you won't know. It'll look and feel like the real network as you log in, do pings, do trace routes. You can't tell if it's the emulated one or not. But we use this for testing every change that goes into production, and we use it for testing new design ideas. The name, which is going to be hard to web search, sadly, is ONE, Open Network Emulator. And it'll be available on the Azure Marketplace in January. It's already available if you'd like to try it. And I'll tell you more about how it works. It supports the major switch vendor, commercial vendors, as well as our own switch software called Sonic. So this is a outreach and invitation to the community to understand how to build networks at massive scale, faithfully, with high fidelity. So let me now get into the first chapter of Rethinking Network Switch OS, SONiC. There are two components here that we're using, and these are all open source, all downloadable from GitHub, including the stuff that I'm talking about in a minute. So one is the SAI, Switch Abstraction Interface. And this was brought to the Open Compute Platform in 2014. And it provides the common APIs and models for allowing the Switch operating system on top of this Switch Abstraction Interface to support multiple ASICs. So we can bring in the next generation of a given ASIC or a different ASIC below. And you've heard from Nick and Ram about amazing ASICs that are coming out. I mean, just incredible. And so we want to be able to, as quickly as possible, bring those ASICs up and get use out of them without disrupting all of our software that we've built up to that point. And this is an open community effort. And I'll talk a little bit about who's in that community in a bit. We also have if you think about that as like a hardware abstraction, and with ASICs below, we need an operating system on top to manage all those resources. And that's what SONiC provides. It's also open. It provides what I think Ram called the data center fabric, the key functionality you need to build a super fast, reliable, low latency fabric in the data center. And it's essentially a Linux box, right? It's built on Linux. It's using the container technology. You can think of anything you can think of, apt-get, whatever you want, your normal Emacs, VI, whatever you use, that you would use on Linux will work on SONiC. And it's using the container technology, so it's very easy to update, very easy to maintain. It's natural. You sit down, and use it without having a large learning curve. It's today built on Debian, although it could be brought up on any modern Linux. Okay. So these are the three things that I talked about earlier as the common goals for a lot of the talks you heard today. We need all three. We can't. I think Aspie pointed out nicely that we can't sacrifice any of these things. So we need velocity. We need to be able to release new features that customers need weekly or faster. If there's a bug or a hotfix we have to do, we have to get that out immediately. It has to be serviceable. So when we release these hotfixes and features, we have to be able to upgrade the hardware and software without anyone noticing. It should be you absorb the new feature and if you were working before, you continue to work. There's no restart or reboot or any disruption. And there's like you would do a container update, Debian container update, instead of a reload of an operating system, which would require a reboot. So velocity, serviceability, and then you got reliability. So this is mission critical. I think all the world's applications are running on this platform. It can't go down, it can't break, it has to be rock solid. So as it grows and improves, there needs to be no customer impact. And those are the three goals that we built SONiC for, to hit all three. The SONiC community includes the companies here down at the silicon ASIC layer, and then we have switch OEMs and ODMs, and then we're using the technologies on top, and then we're working with key partners onto the top right-hand corner, the way I look at the screen. Alibaba, LinkedIn, Tencent, and others. And the Sonic community is growing very fast. I'm hearing about new innovations all the time from the partners. So let me tell you about one application that hits on this reliability theme I want to talk about today. So here's a classic network that you see in a data center called the Cloud Network. By the way, Klaus was a Bell Labs mathematician back in the 50s that figured this stuff out, and he got it right. There are lots of different components here, lots of switches and lots of links, and in many cases, not in all cases, but in many cases, there could be a single point of failure down at the last hop, the last top of rack switch, whether it's at the top of the rack or middle of the rack, the last switch before you hit the servers could be classically a single point of failure. If that switch goes down, then the servers underneath it are isolated. I think Ram talked about the ASICs are getting better. We don't see that many spontaneous failures, but we do need to update the device quite often to light up new features. So a common reason for it to go down is we have to update it and introduce a new feature. And as I mentioned, customers don't have any tolerance for going down. And this is not necessarily just customers like Mayo Clinic. It's also customers like Korean gaming companies. They cannot have any downtime. They cannot have multiple seconds of downtime. So so you have to be able to update the operating system without disruption, and do so where you have single points of failure. How are you going to get that done? Well, I'll tell you about two methods that we use for Sonic, and one called fast reboot and one for faster reboot. The fast reboot, at the time we picked, kind of given the ASIC technology at the time, 30 seconds. 30 seconds is way too long, but it was the mark that we picked at the beginning for the time we could survive data path downtime. It really needs to be sub-second, which is what the second thing is about. So we need to be able, which is called warm reboot, and also you see in the industry something called in-service software upgrade, also hitless reboot, and various things, various other synonyms for the same concept. So it's sub-second upgrade with near zero data path downtime. So here's the basic idea for fast reboot. So let me try to explain. So at the top, there's a control plane, then there's data plane, then there's BGP routing underneath, and time goes left to right in this diagram. And that control plane at the top is the Sonic, the Switch OS control plane. So you can imagine I want to update the Switch OS and get new functionality in there. Let me say one more thing. So in our industry, up till now, to get anything updated on a switch, you had to do a restart of the switch, which is insane, right? I mean, why would you have to do a kernel update to, let's say, update counters like SNMP or BGP, which is an user mode process? It doesn't make any sense. So we don't. Things that we can update in user space, we just do now because it's all containerized and easy to update those kind of things in user space. So we don't have any downtime for that. But there are other functions that will require kernel mode work that could cause data path downtime. So let's say that's the 10% of the cases where we can't just do it without anyone noticing, and there we use fast reboot. So the first step is to just fast reboot the kernel with a kexec, and so the Sonic control plane at that point will start to reboot. So it's down. And then as we move toward the right, Sonic will come back up with the new bits. Okay, and at that point, it's going to, it has, a lot of prep work has gone on ahead of time. So, there's a coordination with other switches in the neighborhood, and those switches know that, hey, this switch is going down. It should, when it comes back up, don't freak out. Do the right thing. Restart gracefully. And at that point, Sonic will say, oh, okay, I need to restart the ASIC. And basically, the ASIC is going to start afresh. Like, hey, what? I have to learn everything now. I don't know anything. And it's going to have to learn all its state again. Now, why do you need to do that? I mean, sometimes when you're updating low-level components, I think, Ram talked about parity error, that kind of thing. If there is a parity error type issue or some sort of low-level issue, you will need just to clear the ASIC. And so that's what will happen here. So because otherwise the error will remain when it comes back up. So the next step is, sadly, there will be data path disruption. And up to, I think, 2 or 3 nines, we have a guarantee, I think it's 3 nines, for no, it can't last longer than 30 seconds to bring the ASIC back and get it reprogrammed. So by this time, Sonic is back. That's the top blue line. And, but the data plane is still down and being reprogrammed. After this, at most 30 seconds, the fast reboot finishes and you're back up. So this is a, when this is an important feature. You might hear about 100G or 400G or I don't know, something else really cool about a switch or an ASIC, but this is the deal. This is why cloud operators will buy a switch or develop technology. They cannot have data path downtime. When it does go down, it has to come back up. Deterministically, this is the most important thing, that you can service the switch. It's not good enough. We want to go faster, and that's what this warm reboot is all about. So it's the same picture and pretty much the same activity, but I don't need to clear the ASIC. And this is often true. We want this always to be true. And the industry is getting better in making this true. So it's the same kind of workflow, except the downtime, that little bit where the light blue, the data plane, and the yellow, the BTP routing, is down, is much less lengthy. It's now sub-second. So if I go through this, we do the K exec kernel restart to start us up. The Sonic control plane will go down. While the Sonic control plane goes down, it's okay. And by the way, it was okay on the other one too. The data was still flowing. It's just the control plane was down. Sonic control plane comes back up. The next step is we do a warm ASIC init. So that means we don't take it fully down. We don't clear it out altogether. What this means is you're going to have a reconciliation problem. So this ASIC will have learned a lot of things, and while the control plane was down, new things happened. So during this reconciliation process, it's going to have to merge in the old information with the new. And out to 2 or 3 nines, this will be sub-second. Okay? Then the reconciliation will be done. This is all orchestrated by the I talked about earlier, the switch abstraction interface. It's got a state-driven model, and everything in it and everything in our design philosophy is designed around servicing. So this is like not just an API, it's helping along the servicing, so this reconciliation goes fast. And then the warm reboot finishes, and Sonic is back, and we're back in business. So we really encourage the entire community here to consume this. Again, it's available on GitHub. It's a open source project. It has its own meetings, its own community. The best way to jump in is to jump in, start, download it, play with it, ask questions. There's a wiki, interact with the community. We welcome, I'm inviting the entire community to use Sonic and improve it with us. So Microsoft is 100% in on Sonic. Next, I want to talk about another chapter in this book about how do you verify your entire network. So the analogy in that that you can make is, you want to go to space, you want to go, run the space shuttle and do something really complex. This is really what network engineering is like. We have incredibly complex networks to run and maintain. It's the vehicle is massive and latest bleeding edge technology, and it has to work. It's the name of that book. Failure is not an option. Yeah, it's just like that. So here's our astronauts. Some of them might be in the audience. We want our network engineers to practice. There's a change manager, wide area networking manager, an optical link manager, a routing protocol coordinator. We want them to practice on this emulator before they try a high-risk network operation, and they do. And they probably did 3 times today. So there's a picture of our global network and one of our data center networks. So what does it look like? So this, really, I wish I had a video to show you, but they go into a room and they do practice. I mean, it's amazing. The team will say, hey, Deepali, take down this link now. Then, hey, Ivan, what's the signal? Do a ping. And they will exactly do a high-risk network operation as they will do in the field, and make sure it works completely before executing it on production. It's quite stunning to watch. So here you want this to be fast. You want to be able to handle networks with thousands of devices and be able to spin that up in minutes. It has to be seamless, easy to deploy, and super high fidelity. The devices have to behave just like they behave in production, down to the very last bug in those devices. And just to give you an idea about our own investment, I won't tell you how much money I spent, but we used 12 million core hours on Azure Network Emulator at last semester, last 6 months. So it's just part of life for us. We don't do anything without running this emulator. And I just told you it's open. It will be open in January on the marketplace, and you can get early versions of it now. So here's a typical scenario. An engineer describes a change, and it's as easy as saying the names of your devices and use your names. And then we suck up those devices and build the emulated topology, called the replica here. And then the next line, moving left to right, the engineer will apply the change, or automation will apply the change. That console that the stick figure is working on looks like and he's on a jump box here, or what we call a jump box at Microsoft. He's logged into a special device that's protected and allows that engineer to log into the network. So he is indeed on that device. It's just the device is not talking to the real network. It is the emulated network. The change is applied, and that'll include the pre and post checks, everything. The show routes. Are they what's expected, and the engineer will verify the routes are as expected. Now there's a whole world of new technology based on forwarding information-based analysis. So, the forwarding information, the fib, is what's really the truth inside every single switch. And you can do all kinds of queries and analysis based on the fib itself. And we do. And that's done through this theorem prover called Z3. That said, a real network engineer is going to do a ping. It's going to do a trace route. It's going to do a show route. Because they want to see, they may believe this theorem prover, maybe they don't. But we will do both. We will do the theorem prover to make sure that, hey, the MTUs are all correct and all the routes, all default routes are advertised where they should be. But the engineer can check themselves. So then we get a pass-fail, and if it fails, we'll change the design. So here's another view of it. The orchestrator will suck up the information from production. We will, going down in a little more detail, we will spin up in Azure a emulated environment on these VMs. We'll use the very same container technology that Deepak and Brandon talked about. We'll use actually nested VMs and Docker containers. We will build a virtual link technology, and we will, let's see if I put on the different binaries from the vendors that are involved. These are the binaries. These are not models. These are the actual binaries. These are the images. So Sonic in there and commercial binaries. Then we'll run the emulation and get the results. So a point that I want to make here is, hey, this idea has been around for a while. So why now? What is it that enables us to do this stuff now? Is it, well, we've got the cloud to do it in. We can burn millions of core hours to get this done. And we've got the VMs, we got the containers, we got all the virtualization technology we need, and we have the network virtualization technologies, which make the virtual network and the physical network one and the same. So the reason it works now is we have the cloud capabilities to get it done now. And so let's get it done. One question you might ask is, well, these networks talk to each other, and don't you have to simulate the entire internet to answer questions? And we can't emulate the entire internet. So there is some technology, and there's a paper about it, where you can draw safe boundaries, safe in the sense that you're not going to make errors around the piece of the network you're going to emulate in order to answer the questions you need to answer to assure the safety of your change. So this is all automated. So once the scope of your question is determined, the software will find the smallest boundary in the network that we can use here. So here in this case, this boundary, there's lots of things that S1 and S2 talk to that don't matter, and L5 and L6 and T5 and T6 don't matter to answer the question. And this allows us to economize the simulation run, get things done fast. So the result will behave exactly as it does for real networks. How do we use this? So in the last semester or two, we completed what we think is the largest network migration ever, anywhere. And it was to give you some idea of how big it was, we moved tens of thousands of circuits in a semester. That's more than we ever moved in the past. We probably deployed more 100 gigabits per second DWDM in that time period, tens of thousands of those components, dense wavelength division multiplexing components that the entire industry deployed anywhere else in that time segment. So we did massive change across the network in order to get regionalization. Customers need the replication to happen safely between their data inside zones with a separation of a millisecond or so. And for that, you need a super fast, super big, super flexible regional network. So we put one in, and no one noticed because of this and other technology, other great optical technology, I should add. So there are these regional backbones went in, and we diverted traffic that had been going over the core network. By core, we mean the wide area network, onto these regional networks. And that's where the one network emulator was being run all the time as we made those changes. I guess this is a little bit old news, but the good news at the time was that and the good news that persists is we have a much better network. And the bad news was at the time that this was high-risk stuff. This was, walking tightrope wires between buildings. This is not easy work to make these massive migrations. And if you're human and doing it, you're going to make mistakes, and there will be impact. Here just a list of things we had to overcome. And there was a long list of things to overcome as we made these changes. The networks were built out at different times. There were little differences, all of which mattered quite a lot. And we had to make sure that these invariants were true as we made the changes, and it was hard. You can get on a whiteboard and convince yourself and still be wrong because there's a bug in the device, okay? That doesn't respect your intent. And before we had one, network engineers had no way to try this stuff out before deployment. So the number 50 is a bit on the low side. We found hundreds of bugs in our configuration, in our management scripts, in the device software itself, in possible operation errors in the procedures of updating the network while we were running the emulator. We know these bugs would have caused at least 5 outages, and we did these migrations without incident in production. So it works. Here's it's now built into the deployment pipeline for our wide area network. And here's the simple loop. So there's a configuration manager. It automates change deployment, builds a replica. The one network emulator will build the forwarding information base and the routing information base. That'll go into the verification engine. If it fails, when we apply those tests, that's that brick wall there, then it won't go through the brick wall. It will go back, and the engineers will work again and make it better, and then try it again. So they have a completely safe and secure a procedure. And if you visit us, we're in building 40 nearby. It could be that some of this is going on right now. If it goes through, everything checks out, then we just bring it into production. Even then, we are paranoid about, and we must know about any glitch in the network. So we monitor these fibs. We continue to run the emulation, the verification on them, and we'll know if there's any error. So again, the invitation is for you to try it. If you have a big network or you would like to try your ideas on a real network, you can hit this mailing list and get the code now for preview. And by the beginning of the year, 2019, you'll be able to pick it off the Azure Marketplace and just run this like we do in Azure. So let's ask again what we're getting here. So you've heard about the challenges of the cloud, and I've talked about the responsibility of the operators. We have really all the world's applications. We indeed do have Mayo Clinic on Azure. We have mission critical work that just has to never go down, has to be flawless, even as we're upgrading it all the time. We have to have velocity, we have to have serviceability, and we have to have reliability, all three. we have to have that sub-second upgrade that Nazim talked about. And so our responsibility, and it's just one, there's others, security is even more important. We have to have super high reliability. And two ways to achieve it, and this is, out of the hundreds of thousands of small things, these are two big things that we've done to achieve it, is to take control of the networking switch OS and go after the most important problems. For example, fast update and many others that were talked about at the other talks. And the great thing is that again, we have new opportunities. We have this new class of ASICs that are coming out that Ram and Nick talked about, and Patty has as well, I believe, or Ori could have talked about. So these are giving us capabilities that we just never had before, and this is why we can now do these things and build a more reliable cloud. And secondly, I talked about the emulator. So you can verify your entire network, take the tiers out of network operations, take the pain out, and that also is made possible by having the cloud there that allows us to emulate every single change at massive scale and make sure it's safe. So it's these things are happening and more. I could go on. I had a long list that got cut from this talk. But these are fantastic things that really use the new capabilities that we have now to build a more reliable cloud. Okay, with that, I'll wrap it up.
Questions?
Hey, so thanks for that. That was great. First, I wanted to commend you on the tremendous success of Sonic. I mean, it just got such widespread adoption use, not only inside Microsoft, but elsewhere. I think it's absolutely fantastic. It's been much needed. Somebody needed to step up, take this seriously, devote the attention and the resources to it. And it's fantastic to see that happening. I've been familiar with the Crystal Network emulator. I hadn't quite realized that it had grown up so much into something that you were using on such a big scale. I assume then that it will be available for testing of Sonic, because presumably it's a fantastic environment for testing, not only for your own use, but for the community as a whole. Is that the plan? Will it be sort of integrated as part of the overall testing plan and release
absolutely.
plan for Sonic?
Yeah, I mean, with Sonic, there are even more opportunities because it's open source and it's out there. But yeah, I mean, all you need here to test is provide your switch OS in a Docker container or in a VM, and Sonic is built that way. So yes, it's Sonic ready out the gate, and we test Sonic on this. Yeah.
And you mentioned the executables of OEM boxes. You particularly mentioned Arista and Cisco.
Yeah.
So they will be available as part of the sort of the general product that other people can use, the open product.
Yeah.
Presumably not the open source of their.
Yeah, I think there are a few signatures remaining on that, but
okay.
that's absolutely going to happen.
That's great. You can imagine for researchers, for graduate students, this is fantastic as well, right? So that's going to be wonderful. Thank you.
Thank you for the very good talk. One question I had about the ability to upgrade in an environment which is active and live. There were a lot of activity in the past around the high-end routers to try and do non-stop forwarding, which means that you don't even have that warm boot in the middle.
Yeah.
And I was wondering if you have any direction to actually get to that point that we have non-stop forwarding in Sonic.
Yeah, The nonstop forwarding and that kind of stuff that I had seen in the past had been a bit of a black box to us. Here we're throwing, essentially hypervisor techniques. We're taking techniques out of the computing world, and we don't think there's anything necessarily special about the ASIC. There's save restore techniques and reconciliation techniques that our colleagues in compute have figured out, and we adapt those. I think in the context of a network, there's more to it in the sense that, like I said, you do BGP graceful restarts, or you tell your neighbors, hey, I'll be back. I'm going down, I'm going away for a little bit, and so they don't freak out, and you keep the keep alive and the echoes and things like that going. So there's some enhancements. But I think the big story is, and built into Sonic is, hey, it's a Linux device. It's nothing scary. It's something familiar. You should be able to update your Linux device wherever it happens to be sub-second, and we do. Yeah.
Okay, if there are no more questions, let's thank Albert. So we now have a reception just next door, so I'll ask each one of you to head to the reception. We'll be sending out a survey. We would appreciate if you could fill out the survey and let us know how you like the event and other comments for improvement suggestions.
I want to echo that. This is our first time trying this. I think, I learned a lot. I think people were very open, and I think more open than I expected about the problems that they have and the techniques that they have and what they're offering the community. So we really want to know how we can grow and get better. We tried new things. Again, we talk a lot about diversity and inclusion all the time here. So we thought, well, let's lead with that. Let's not have a technical session and on the side diversity and inclusion. Let's put that in the middle of the conference. So these are ideas we want your feedback on. We want to know how it works out and how we should grow this thing. Thanks.